you very much for the introduction. I intention to put UMass Law and Stevenson here because right now I'm working UMass Law, and which is close to Boston area. I told Bella that I thought the coldest winter is in Massachusetts. But once I come here, go to Berkeley, I think the coldest winter is the summer in Berkeley. It's really cold here. Okay, so with that goal in mind, let's move on. So today's talk on the hardware software co-optimized block analytics. Before I talk about my talk, this is a brief introduction about my lab. We have a couple of students, and we got a couple of awards from ASF and DOE, and donations from industry partnerships. So with that, we got the champion of 2018 MIT Docker Amazon Graph Challenge. Also the #1 most energy efficient graph proposal of 2014. We also do open source the software, so we see our language duplication work is being adopted by Debian, Aurora, and Ubuntu. Also, my graph algorithms is being adopted by NVIDIA and Intel for their test. So, today's talk is about data, right? So it's about graph computing or data in general. So I think data is everywhere. So when I go Google and try to search what examples, I say, okay, there's a lot of examples. So why don't I just put my papers screenshot instead of it? I do social network. I also do blockchain analysis. I also do the cardiac, the fancy video over there is the cardiac dynamics simulation, and knowledge graph or bug detection or Internet of Things. Well, barely in this gigantic graph is the insights to advance our community to make the society much better for our daily life. Well, because graph is gigantic, then we say, okay, we cannot just use this traditional hardware anymore. We have to move on to those emerging hardware because they are designed to solve this gigantic graphs or data set. Well, the first thing we take a look into is GPU. The motivation is very, one motivation is that, and for the HPC area, I think we can take a look at those top 500 rankings. Well, if you take a look at specifically today's screenshot, you see the majority of those top supercomputers are using GPUs. So that means GPUs really getting into the powerful domain of computing. Well, or I bet everybody here knows machine learning, right? No matter if you're doing machine learning or not. But actually, you want to see that all those machine learning tools, they're either fully supporting GPU or partially try to support GPU. So we say GPUs in HPC area, GPU is supporting a lot of softwares, so it's very helpful for us to take a look at it and see whether we can get benefit from it, and we can benefit the community at a lot. Well, beyond this kind of GPU I also use other hardwares, in particular HPC, HMC, FPGA, and SSD, particularly from Samsung. Okay, I'll mention that. And also NVIDIA. So, taking all of them together, my research is at the intersection of hardware, software, and data. So we tackle graph data, a lot of graph data, as well as those non-connected data. Well, we also use GPU which is emerging hardware, as well as configuring those new hardware to solve something, like FPGA I'm going to talk today. Well, with the hardware, they cannot just sit there and help you, right? So you need to use some software designs, like make better algorithm to suit GPU. Like previously, serial algorithm can only work on CPU. When you do some more massively parallel algorithm that can work on GPU or FPGA, or you have to design better cache or better I/O, which is system challenges you want to deal with. So we say today's talk is hardware software co-design data analytics and graph analytics to extract some insights. With that being said, I'm going to briefly talk about three of my papers published recently or a couple of years ago. So the first talk is about using GPU to solve graph computing, or we say SymDX, programming and processing graph analytics on GPUs. I'm going to explain why it's called SymDX later. So it's about GPU and graph. So let's give a little bit of background. So what is GPU and what is graph computing, and then we can move on. So the first thing I put in here is we see GPU has very favorable computing power and data delivery power, right? It's shown here. Why we have this very good computing power and data delivery throughput? It's generated from the hardware design, which is majority of you guys are also focusing on hardware design. So they have hierarchical processors, called multiprocessors or SMX from 0 to a couple, and instead of it, they have a couple of simplified product cores. Taken together, you have more than 5,000 cores from V100 GPUs. It's pretty powerful, a lot of cores. And instead of it, you have those hierarchical memory components, registers, shared memory, L2 cache, and global memory. The access lattices are shown here from 0 cycles when you access the register, because it's like their implementation to 400 cycles. So you can see that there's a very important thing over there, that is they are hierarchical. Hardware hierarchical in terms of processor and memory. So that introduced something, well, I would say it's pretty much very necessary for PowerChip, that is they introduce the same architecture. Because you have so many cores, right? Like a general has so many soldiers, you cannot command every soldier individually. They have to be in groups, so you can manage more efficiently. Then they introduce SIMD, which is they group every 32 threads together into a single group. And they have to execute the same instruction, probably on different data simultaneously, so that you schedule a group of people at a time. So it's more efficient for you to schedule instead of schedule a single people at a time. Well, with that being said, if you cannot, your application cannot fit in that paradigm, then you're going to suffer from performance drop. Right? This is something the paper is going to be talking about. Well, here I want to talk about one more thing. That is, in memory access pattern, you have the same SIMD philosophy. That is, you want adjacent data, consecutive threads to access adjacent data. Well, if consecutive threads access non-adjacent data, you are suffering from spread memory access and performance drop. So this means GPU is very powerful, but you have to dance with some restrictions. You cannot dance freestyle. Right? Okay, so let's see how we dance with something in our hand. So we want to map graph computing on GPU. So first thing for GPU, to motivate GPU computing in general purpose is base matrix computing. Right? We say when you map base matrix on GPU, it's very straightforward. It's very regular, one-to-one. Well, if you map graph on GPU, it becomes a little bit twisted. So in summarization, we say GPU is SIMD in nature, a graph is complex in nature. If you still remember, when you're learning algorithms, graph algorithms typically appear in the last chapter, right? So which implies probably it's more complex than other algorithms. Well, SIMDX is here to bridge the gap between SIMD and complex graph computing. Well, we're going to discuss about GPU. Let's take a little bit look at some popular graph algorithms, like single source shortest path. So here we have A to I, 9 vertices, 9 circuits, and 1 vertex. And the line between those vertex are the edge width or distance, you can see. Here we're using single source shortest path to illustrate the computing. So, assuming that the distance array or metadata array is shown below, starting track also for single source shortest path computing from vertex A, so the distance of A is 0, and then you check A's neighbor, you get B and D, whose distance are 5 and 1. You keep going. So here, the darker brown is the current active vertex. Well, the slightly lighter brown is the next or just being updated vertex, which is going to be active next iteration. So here, when you proceed next iteration, you work on B and D, and you check the distance of E and C. The updated distance in the metadata array. You keep going until you figure out there's no update going to appear over there. You can either use the actual algorithm which has no parallelism because we only work on one vertex at a time. That vertex is the shortest distance right now. Or you can use BFS, you let whatever who get this distance updated work starting together, and then we got a lot of repeated updating, right? So in summarization, we see every computation, you only have a few vertices, a portion of the data is active. It's not that you have to just see word count. Every vertex is active, every data is active in every iteration. Here, it's only a portion of them is active. You don't have to manage them in order to map them on the GPU better. And second is, different vertices are different. If you take a look at a Twitter graph, maybe Lady Gaga has millions of vertices, neighbors, but I just have 5 followers. So that means if you treat them the same, you're going to suffer from local imbalance problem, right? And the third thing is you have to do synchronization from one iteration to another iteration in order to make a better performance, right? So we say those are the challenges you want to deal with in order to bridge the gap between GPU and graph computing. So I can do a little bit of technical stuff. So bear with me, okay? So see how it works. Still using the same graph for the convenience of your memory, right? So assuming we're working on EMC, and then we're going to update the distance of B, F, G, H, I, and generate the frontiers of B, F, G, H, I. So how it works in existing work. So you have EMC, then you have a couple threads that you can look through this EMC, and then you're going to check the neighbors of the EMC, which is BF connecting to EC, and then B, F, G, H, I connecting to E, and then you gather the source and destination together. Like C is connecting to CB and CF, and E is connecting to the rest of it. You gather them into active neighbor list, and then you work on the neighbor list to update the distance array, right? Once the one is getting updated, you see it's going to be active in next iteration. So you put them together in the next active list. So this is how the current work, the work before this work in the graph computing, like people 5 and people 16. But we say first, gathering what active list, neighbor list can consume a lot of memory because it's source and destination. You can have all those activities being active at a single iteration, according to the power of graph computation. And second, you have to figure out those active neighbor lists as well as the current distance array in order to generate the next active list. So it's a lot of redundant work. And you also generate out of order active vertices. It should be A, B, C, D. Well, here is B, F, H, G, I. So those vertices that's smaller appear later. So it's out of order. You're going to make your memorized pattern very bad in the next iteration, right? So instead of asking to memorize those examples and summarize them for your better, understanding, it's you have a current active vertices, you load the neighbors simultaneously, and then you construct an active neighbor list, and then you filter out those neighbor lists, and then you generate next active list. Here, the pink color means it's pretty bad because it consumes too much memory, or because it generates those out of order active vertices. So instead of doing that, let's see how we propose to do it using GPU's specific design. So assuming we have active vertices EMC, we look through it and as well as working on neighbor list. So this time we say, okay, let's directly update those distance array. Right? So we do not fetch them and stage them into another memory space, we just directly update it. And then after we update it, we do a comparison between current distance array and previous distance array and do Valade failure. It's a GPU primitive. It sort of collaboratively asks two threads to work on a single two atoms together so that it can generate the data in sequential order. So eventually you get this thread names B, F, G, H, I, and you put them together. You see that you do not have to stage those neighbor lists, but here we deal with the local imbalance problem by using different hierarchies of threads of GPU to balance the workload. So it avoids those possible jeopardy or problem that you have to work in previously. Well, the second thing is we only have to do one-step filtering and using Lec filter to generate in-order active vortices. So to summarize, we have current active vortices, then we load neighbors in, and we simultaneously update the metadata by balancing the workload. So you didn't suffer from workload that problem. And then we filter out those metadata using Lec filter so that the same group can generate in-order active list, right? This is a little bit technical. If you want to know more things, this is why open source in GitHub, and also you can shoot me an email if you want to know more details. So we say another way of doing this is you have a couple of active vortices. I mean, here you have a very few number of active vortices, and then you say, okay, scan through the distance array may take a lot of time. So what we do is we use atomic operation to do that. So you use atomic operation to update the current distance array, and then you put the active vortices into the next active list. So you do not have to scan through the current distance array. Oh, I'm doing something here. So here, in current distance array, you do not have to scan through it in order to generate thread in because you use atomic operation to generate them, right? So in summarization, here you know the neighbor and you automatically update the status atomically, update the status array or metadata and then generate the active list. You avoid scanning the status array. So in summarization, we have compared against existing batch filter, which is the existing work, and we introduced some new work like about Lec filter and atomic update to generate the worklist faster so that you can balance the workload better. We have other works discussing about technical details, but I will not go through all of them. Here, I am only talking about a little bit about programming stuff, which is high-level things that can sort of benefit those normal users who's not rough expertise can also benefit from this. So, assuming you have 0 to 7 8 vortices, and the shells instead of the cube means the workload. So you have a higher workload and lower workload. So you classify and filter them into different buckets. One is 0 and 3 is like low workload, and 1 and 5 are tend to be high workload. Then you have synchronization, and you map them into different number of GPUs. Number of GPU cores, so which means you have lighter workloads, so you map them into smaller number of cores. If you have higher ones, then you map them into more cores. By doing that, it means the core, that no matter working on which task, they experience similar amount of workload, right? Well, this is the philosophy of this design, and then we want to tell you that you do not need to be like an expert of GPU in order to leverage this, because you only have to tell me which vertex is active. I'm going to do the filter and classify for you. And then you also only have to tell me what kind of computation you want to do. And then how to balance the workload, how to get the data, I can also get that with you. Similarly for combine. So here I try to sell that SymDX is very complex internally, but APIs to users is pretty simple because we only grasp those essential functionality APIs for you, not the performance wise. So you only have to define ACC. Other things are done by SymDX. So taking all of them together, we see very decent performance gains comparing to Galrock and Galois, which are published in PCOP and SOSP. The x-axis is the graph data set from Facebook all the way down to Twitter, and the y-axis is the time consumption in milliseconds for 5 iterations of computation. Well, PageRank is definitely very straightforward. If you go to BFS, which is a breadth first search, it's another very classical graph algorithm. We say we're also getting a good edge over Galrock and Galois. Well, if you've been very particularly picking on the performance, you see the RD dataset, Galois actually is faster than SymDX, which is
Well, actually, the reason is because our design is particularly for power law graph, which has a skewed degree distribution. But here, then our D graph, which has a uniform degree distribution, that means you spend a lot of energy, but just generate the same workload as before. So that's why we didn't experience good performance gains here. This is the first thing I want to give you. The takeaway is very simple, is GPU is very powerful, right? But you cannot do freestyle dancing. You have to obey something from GPU. Either you suffer from a lot of programming difficulty, or you suffer from performance drop. So then it brings us to the second topic. Can we design some hardware for our programming, for our graph computing? So we consult FPGA. It's a lot about a graph. So not a graph example. So we have a toy graph here, have 0 to 5 vertices and a couple of edges between them. Assuming we want to do BFS, so we're starting from 0, and then we traverse its neighbors 1 and 3, keep going until we generate a valid BFS tree here. So this is how it works in our human's brain. So let's see how computers work on it. Computers does not have geographical storage. It does not know that 1 and 4 or 0 are close by, so virtually you see that, but computers cannot do that. Computers, as you guys know, majority of us are hardware designers, so we know that they store the data either in 1-dimensional or 3-dimensional at most, I think, array. So assuming right now we still store it in 1-dimensional array, so you store the neighbor of 0, 1, 3, and then you store the neighbor of 1, which is 0, 2, 4, etc. This is how you store the graph in computers. Well, assuming you are traversing the graph, this is how you're going to go through the traversal. You go to 0's neighbor and 1's neighbor, and then you jump to 3's neighbor, and then you come back to 2 and 4 and 5. So you see a little bit twisted, right? It's not good because it's twisted, so that means the memories, the prefetches or whatever designs you have before may not work for this random access pattern. Well, another worse news I want to tell you is when you access the neighbors and check whether they are first time visited, the access pattern is even more twisted. Okay, I think you got it, right? So it means you accessing the neighbors, 0's neighbor is 1 and 3, so use 1 and 3 as index to check the status of 1 and 3. So you have to go to the cell 0 of the status array and cell 3 of the status array. You keep going back and forth. So we say graph data is random, and the metadata access or status array access is even more random. So here, then it brings us to this topic. We have a doctor BFS, which means we have to design the processor with data-centric in mind. So that's why we call it doctor BFS. It's not they've been getting a doctor degree. Okay, so let's move on. So how we deal with it. According to Amdahl's law, we always solve the most challenging problem first. Then let's solve the status array first, right? Well, before we solve that, let's take a look at the FPGA, a little bit background. I know a lot of you guys are being very expert about it. Just bear with me for 5 minutes. Let's go through it. So it's a very nice play together, like a wall over there. You have 3 components. First is the CLB, or configurable logical block. You have LOT, D flop-flops, or adder and multiplexer for you to do those arithmetic or logical component computation design. And those green ones are block RAM, where it's on chip scratchpad. It's very fast. And also there are those things that I didn't draw out here, but it takes majority of the space. That's the interconnect between those square bracket and those block RAMs, right? So here we're mostly focusing on one thing, that is the large, controllable, and bit addressable on-chip block RAM, because we want to cache those status array on chip, so that no matter how random it is, it's faster, right? This is where we're starting from. So then we say, okay, why don't we cache the status array on chip? It's integer. Well, if it's random, it's on chip, it's like 10 times better than you access it from DRAM. Okay, and also, in order to solve larger graphs, we can also do bitwise things. So you starting from a byte to a bit, so you can store the graph which has 8 times larger vertices. You may still question, okay, what about the graph is even larger, right? You can never hold it by compressing. So then we consult the software designs. We say, okay, why don't we partition the graph vertically? So whenever you are working on 0, 1, 2, you never work on 3, 4, 5. When you are working on 3, 4, 5, you never work on 0, 2, 2. So this partition, vertical partition, gonna guarantee that. So when you are working on the first partition, you only update the status of, here, the matrix is a graph, right? Every row is a source, every column is a destination. Every one means that's an edge, okay? So when you're working on the first partition, you're gonna only update the destination vertices from 0 to 2. When you're working on the second partition, you only work on the destination of 3 to 5. You keep going like that, right? So you will never go beyond when you're accessing status. If you have a larger graph, I do more partitions, right? So by doing this, we see the performance of metadata access is getting much better. Then it's a time we can proceed to next data, that is graph data access. So how we do that, this is very straightforward comparing to, it's very similar to the storage. That is, we combine those access together. If it's two separate transactions, we combine them up to the bandwidth of the bus, right? And second design is, instead of every vertex processor issue a transaction to memory channel, we say, okay, why don't we just, every channel has one provider, so that whatever request you have, I just provide a single transaction and move it back to on chip, and then you can do the computation or dispatching on chip. And also you can do implicit or transparent workload balancing between different memory channels. Okay, I know it's very technical. Let's see a little bit of animation to relax. Okay, see how it works in animation-wise. So we see we have the left side is the off-chip memory, and the right side is the on-chip fabricate. So you have the status array and the graph data over there, assuming you worked already of the level 0 and level 1. And then, so level 2 gonna focus on the vertices, that's who get the status updated. So that's, you move these two on chip, and then you do XOR, you figure out vertex 1 is just updated. And then you fetch the neighbor of vertex 1 because you do 1D partitioning, vertical partition, so you only know half of it. On chip, right, you do a single transaction. Not every processor issue a transaction. Here you have vertex processor 0 to vertex processor 15. You do not ask all of them to issue a request. Instead, you fetch all of them on chip, and then you dispatch it. And then they go ahead, update the status in the on-chip block RAM, and then you write it back, right? This is how we try to design this kind of processors. By putting those kind of things together, we do see pretty good performance gains comparing to existing work like Doris, BFS, and Mulumuru, that for x-axis is different synthetic graph from graph 500, and y-axis is the traversal rate. Here we do not use flops because graph computing is more data-centric, so we use median traverse edges per second, or MTAPs. Higher is better. We see Dr. BFS is always better than state-of-the-art Taurus BFS or Muruglu. And later, we've also been asked to test the efficiency of FPGA, because when you go to HPC area, when we talk about FPGA, everybody's gonna think it's an accelerator. So they're gonna say, okay, you tested on FPGA and GPU is so popular, why don't you test it on GPU as well? So this is the comments we get from a reviewer. And then we just go ahead and test the efficiency, because we see that FPGA just has tens of GB per second throughput. GPU has hundreds. Then we can definitely not beat the performance. So we figure out, well, actually we can compare the efficiency. Which one has a higher efficiency? Well, we say we get a better memory throughput utilization comparing to GPU state-of-the-art enterprise, which is also my work. We published in 15. It's definitely true. It's not a sort of skewed data, okay? So We solve GPU, we solve FPGA, and the last thing I want to share with you is about solving big graph, which is also using SSD to solve it. Why we want to solve big graph? It's very straightforward because graph is getting bigger and bigger. Starting from 28 to recently, you see the graph size have climbing to billions of users. Think about maybe Lady Gaga is inside of it. They have millions of edges. So you have so many edges to billions of users. Then you have trillions of edges or even more. Well, this is going to make you to use sort of some high-end shared memory systems to solve it, but it's going to be very pricey, right? Or you can use distributed system, hundreds of nodes. It's also going to be very pricey. Or you can use external memory. Using SSD or HDD, it's definitely more cost-effective. But the performance-wise, external memory gonna be pretty suffering because you have to access the data in a random way. How are you gonna deal with it? Another important thing is when you talk about programmability, external memory is gonna be very complicated because you have to deal with those debugging. And for me, when I consult those AIO or asynchronous IO, I see there's a lack of glibc debugging support. So you have to guess what's going on, what's wrong with it, right? And very few people doing programming in that level. So there's very few comments or symposium to support you any advice to debug your code. Actually, it takes me 3 months to put it together. So with that being said, our goal is faster, cheaper, and easier to use. Okay, so let's see how we achieve the goal. So first, let's talk about the external memory, how the existing work deal with it. So assuming you have a couple of active vertices of V5 to V3, then instead of fetching a neighbor previously, right now you have to translate it into different blocks, right? Block 7, block 15, and etc. And then you have put it into Linux block list. You do a little bit of sorting, and then duplication, and then you merge them together, and you issue the request to graph data that's on HDD or hard drive. So we see this random I/O. Then existing work like OSDI 12 and SOSP 13, they said, okay, why don't we just go ahead and fetch one data in? We don't care about which data you ask for. I just fetch the entire graph data in memory and for you to compute. This is actually very rational design. Because when you take a look at those bandwidth report from those papers, you see that the sequential I/O is like hundreds of megabytes per second, but the random I/O is less than 1 megabyte per second in that time. Well, if you take a look at SSD, the selective I/O or random I/O is comparatively much better, I would say, much better than HDD. It's almost comparable to the sequential I/O. Then it's the time for us to think about it. Can we actually support selective I/O, right? Maybe we change a little bit of the software, but we can definitely save a lot of those useless data loading, right? How we deal with it, it's still using a status array. Assuming we have active vertices V5 to V3 on the top, and in the bottom we have the graph data as before, but we store it on SSD, and then we use the bitmap to mark which bit we should use. We should load, like true or false. True means we want to load it. Well, by marking this, you definitely can do a global range I/O adjustment, and also you can merge them because they are globally sorted. And also we see that even for 250 GB SSD, the bitmap is less than 100 megabyte, or I think it's around 32 megabyte or something like that. So it can perfectly, or majority of them can perfectly fit in ILC. So when you have those bitmap autonomy operation, it's still pretty fast, can be handled by CPUs. So there's no redundant I/O, definitely. And then here we sort of use AIO to redesign those Linux I/O stack so that your computation can be better deal with. So how we do that, we open the file, we do a little bit of POSIX memory alignment, and we set up the IO context, and then we assume which vertex is active, and then we do a little bit of alignment, and we fetch the data by IO subbit and IO pool, and then we do the computation. So here I try to tell you that using Linux AIO instead of POSIX AIO, it's faster definitely because you avoid double copy, but it does not have those error support. It takes a lot of energy for you to figure out what's going on there by guessing what's wrong, right? So the programming is pretty complicated instead of seeing that. Then we say, okay, why don't we propose a framework that I/O can be dealt with by us? You only have to focus on the computation. How we do that is here on the right side. You have an iterator, and then you just keep asking for more. If the iterator has more data for you to process, you keep processing it. You do not have to deal with the I/O stuff. You do not have to debugging or anything like that, and it works pretty well. We tested for 6 graph algorithms, like APSP or pair shortest path, BFS or breadth first search, until sparse matrix vector multiplication or SPMV. The lines of code is pretty much similar to in-memory computing, and the block request SSDs are dealt with by us. We use 16 Samsung Evo 500 SSDs, and they give us pretty good performance. So taking all of them together, we also evaluate that on a couple of graph algorithms for the data set that has 1 billion vertices and 32 billion edges. It should consume like 500 GB memory, but we only give it 16 GB memory and the 16 SSDs. Well, our performance-wise, because we do some other optimization, they're gonna, it's in the paper, we do memory optimization and cache optimization. We see that our performance is even better than distributed systems as well as shared memory systems. This is the speed up. So when you zoom in, you will figure out actually our BFS is worse and the WCC is also worse than the shared memory system. The reason is because we didn't use the same algorithm, which we are working on right now using better addressable SSDs. Because with that algorithm, you have to use better addressable SSD in order to enhance the efficiency. For more details, we can talk about later. Okay, so these are our 3 sort of contributions. First is we redesigned IO stack, do some AIO stuff, wrappers, and then we do easy programming. We also deal with the memory components because I didn't sort of cover those memory stuff. If you are interested, you can take a look at the paper. We do huge page support and page coloring, sometimes selectively. So, okay. All right, so we finished the existing work. Let's move on to future work. Well, actually, when I was talking to Ada, I figured out that you guys are doing something about smart SSD, which is something that I've been working on a long time back, but I didn't know that you have this kind of devices before. So what we do is we do graph computing with SSD, CPU, and FPGA. So there's a multiple hop, like a jump from one SSD to CPU memory and then to FPGA. Well, it's low latency, low throughput, and power consuming. We say if you have the smart SSD, which I see that from Samsung's announcement, which is very impressive, right? So it has faster throughput if you aggregate them together. And you can also do direct block device access from FPGA. You can deal with some raw device programming error debugging sort of research. You can also do some indexing for better data access. Well, this is a little bit abstracting, so let's move on to the detailed stuff. For example, I figured out when you're doing graph computing, actually, it's better you sort. Here, I show it here. It's better you sort the active vertices and the neighbor list, and then push them into the SSD. Even sorting takes longer time, right? Well, currently, I can only use FPGA. It's a paper in pipe. And I figure out if we can directly go from FPGA to SSD, and if we have more SSDs over there, then we can directly customize FPGA for the sorting of graph computing. Because why we do sorting is because we want to fit into the cache line. And then we can also do, sorry, I know it doesn't work. So we know that we do not need to sort it precisely in the sorted order. We can sort it in a fuzzy order so that you only sort until the 64 elements are in the same range. Then you do not have to sort in the range because no matter what, they're in the same cache line, right? And also we figured out it's a philosophy change by using sorting because it can change from push to pull simultaneously to avoid those atomic operations. Because I think I have another related work, so I will just stop it here. And another work is about graph analytics. So why we do graph learning? Because first, a lot of data set come in the format of graph, like the blockchain stuff, which we have a paper submitted, accepted in CNS recently. And when you are doing NLP processing, it's also processing of the graph data set. Where you do robotics, it also processing knowledge graph. So we see there's a lot of applications over there. Well, you may think, okay, why don't we just use the deep neural network, which is like LSTM or convolutional neural network or GAN or something like that. Well, we see that it's working pretty well for those grid data or non-connected data, such as ImageNet or reinforcement learning for the chase or Chinese Go, and then NLP or speech recognition. But we see that if you apply this on graph, it will not work. Why? Because you have the same graph, but you have totally different labeling. Let's say you have a 0 to 9, 10 vertices on the top left, as well as 0 to 9, 10 vertices on bottom left. They are the same topology. They should be the same. But if you translate that into matrix format, they're totally different, right? The two matrices are different. Well, then you may recognize them into different shape, but actually they're the same thing, right? So this is some sort of, you feel like it's very straightforward, but this is one example to tell you that using the traditional graph deep neural network may not work well for the graph learning. So then I think there's a couple folks from graph signal processing or GSP in 2009. They say, okay, why don't we convert the graph into signal domain or frequency domain and do the computation? How it works is they use the graph to define the way you do the computation. So basically, assuming you have the first 5 and then you work on 2, 3, 8. So, okay, so the rest of 1 over square of d multiply a multiply 1 over square of d and multiply hi, it's basically gathering the neighbors embedding from gathering an embedding from the neighbors because it's A multiply H. H is the embedding of every node. A is the adjacency matrix. Well, you may say, okay, is it like fabricated? You intentionally do it like that? Well, actually, this is backed up by the spectral graph theory. They use Taylor expansion and Chebyshev estimation to arrive at this point that's explainable. They say, okay, because we use expansion to a lot of signals and then they only take the first 2 signals, they say it's exactly 1 over d multiply a and multiply 1 over d. So it shows you can use a graph-defined neural network to do the embedding aggregation or like a PageRank style, right? And then you go through the ReLU, which is like a deep neural network. Okay, I have the explanation here. If you want multiple hopes, then you can continue that. You want more, you can do more, so it goes to deep neural network. But actually, right now, they only do like 3 layers. I think my slides end here, but I want to show that it can work. So here, this is the most computation extensive part. How are you going to deal with it? We're going to use some FPGA and GPU to deal with it. And the second thing is when the graph grows huge, then you have to sample it and partition it. So then we introduce some random work stuff to partition the matrix so that you can fit them into the memory, and then you introduce some caching stuff I think that's pretty much about it. Thank you.